Hello. In this video, we'll focus on complex numbers. Uh, Complex numbers allow us to expand our work with radicals to include square root of negative numbers and to solve some equations that will lead to the square root of negative numbers. Um, we know that if we have the square root of, let's say, negative 16, that currently we say that there is no real number that when multiplied by itself will give 16, negative 16. So this, from what we say, from what we learned so far, is not possible, right? And we should really say there are no real numbers. Yeah? There are no real number when multiplied by itself. However, yeah, um, with what we're about to learn today, we will see that we can work with this by introducing what is called complex numbers. In addition, if you look at an equation, x squared is equal to negative 25. We say this has no real number solution. Yeah, and this is because the square root of a real number is always positive, right? The square root of the real number should be positive. Yeah. So we have been unable to work with square roots of negative numbers. Yeah. Complex numbers now will give us the ability to work with these. Yeah. Now the number I, yeah, letter I, lowercase, is such that I is equal to the square root of negative 1. Yeah? I is equal to the square root of negative 1. And this allows us to work with square root of negatives. And if you don't quite see what I'm saying is yet, if I go back to my example, okay, the square root of negative 16, what I will do is take out the negative. So I will break this into two roots. Okay. The negative 1 times the square root of 16. And I now know, based on this here, that the square root of negative 1 is I. So this here becomes I. And we know the square root of 16 is 4. So we have I times 4. And generally, we always write the coefficient first, just like when you write 2 times x, you don't write x2, right? So this is equal to 4I. So it helps us to get an answer, but that answer is not real because we have embedded I into our answer here. So that will help us, yeah, tremendously. This will help us. Now, generally, you don't have to, I mean, I always recommend to show steps at first, but we tend to skip that sometimes, yeah. And I'll show you in my next example. We don't have to write it, we can just pull it out and write I. Yeah. If we look at this example here, yeah, the square root of -25. Yeah. So because we know that there is a negative here, that negative automatically comes out and can be written as I times the square root of 25. So there is like a hidden step. There's a hidden step here, right? There's a hidden step. And that hidden step is that we took the square root of -25, we broke it up into two roots, -1 times the root of 25. And then this here is my I, root 25. Okay. So once we see that negative, we take the negative out and the negative becomes I. And then we can simplify. The square root of 25 becomes I in the outside times 5. Yeah. And that becomes 5I. So that's what I'm saying over here, right? Sometimes you can just ignore that step and just write I, okay, as I did in this second example here. Now, be careful because in addition to simplifying, sometimes you may have to simplify the radical. For example, if I have the square root of -12, well, the negative comes out as I, so this becomes I root 12. And then you still have to simplify root 12 because root 12 is the same as root 4 times root 3. And don't forget I have to bring down the I. And then the root of 4 becomes 2. Okay, these are all multiplication. And the root of 3 we don't know. So then we rewrite this as 2I radical 3. Okay. Now, if we assume all the properties of exponents hold when the base is I, we can write any power of I, yeah, as I, -1, -I, or I, using the fact that if we have I is equal to the square root of -1, okay, we can square both sides, right? So if we square both sides, we end up with I, but let's square both sides now. Okay. And if we square both sides, we end up with I squared. And remember that the square will cancel out the square root, and that leaves us with -1. So I square happens to be -1. So we're sort of like building here, right? So now we know I is equal to the just I, right? Which is equal to the square root of -1. We know I square is now equal to -1. Yeah. And we can continue doing this and we can find what is I cube, what is I to the 4th, and this can go on and on and on. Yeah. So there's a little techniques in how you simplify these things. So let's look at that. Well, I square will always help you, okay? So if the power is odd, I cube, let's say, we want to rewrite this using an even and an odd power. And we'll do that by writing I squared times I to the 1. Because remember, right, recall, when the base is the same, you add the power. So 2 plus 1, this becomes I 2 plus 1, which becomes I to the 3rd. Likewise, if I have I to the 4th, I to the 4th is equal to I squared times I squared. Okay. And if I have I to the 5th, this becomes I to the 4th times I. So anytime you have an odd power, the I will always stand out by itself. Okay. So why are we showing you this? Well, so just keep in mind this can go on and on and on. Okay. But at certain point, it gets too complicated to write these things out. So we can simplify a better way. So if I ask you, right, what is I? So can you simplify I to the 50th power? And just to go back for a second, any one of these results here, the answers will be I or minus I or 1 or minus 1. These are the only 4 choices for answers. Okay? Those are your only 4 choices. Now, if I ask you to simplify I to the 50th power, well, let's rewrite this as I. So rewrite, and I said I square is very important here, as I to the 2nd power raised to some power. So what do you multiply 2 by to get 50? Okay? And that becomes 25. Okay? We know I square is minus 1. So minus 1 now raised to any odd power, okay? Minus 1 raised to an odd power is equal to minus 1. So first thing to note, right? If the power is even, okay, then I could just write I squared times what number? But if the power is odd, it's not divisible by 2, right? And I'll put a side-by-side working here. If I ask you to simplify, let's say I to the 21st power. Notice in this example, my power is an odd number. So when it's an odd number, you have some simplification to do. You will have to break it up, okay? You will have to break it up as I to the 20th power times I, because that is the same as I to the 21st power. And then we rewrite the even side. We rewrite this. And if we rewrite that, we get I squared, okay, raised to the 20, to the 10 power, to the 10 power. because 2 times 10 will give you 20. And we know that, don't forget, we have to bring down our I. Right? We know the inside I squared is minus 1. So minus 1 now raised to an even power. And if you have any negative raised to an even, that will produce a positive result. So this becomes positive 1 times I, which is equal to I. So in one answer we have minus 1, in the other answer we have I. So this will take some practice. Okay, this will definitely take some practice. So let's do some more examples. Simplify. How about if I have I to 40? Well, observe, this is even. So I can jump straight ahead and rewrite this as I square raised to some power. So we rewrite as I squared raised to 20th power. Okay, because 2 times 20 is 40. I square we know is negative 1. So negative 1 raised to the 20th power. And any negative raised to an even power becomes positive. So this here is equal to 1. Okay. Example, simplify. Let's say I to the 101 power. Well, 101 is not even. Okay, it's not divisible by 2. So I will rewrite this as I to the 100 times I, which is the same as I to the 101. And then this here we can rewrite. Okay? We'll rewrite this piece. So this becomes I squared raised to the 50th power. And don't forget the I we have here. And then we know that I squared is minus 1. So what is minus 1 now raised to the 50th power? Okay, minus 1 to the 50th power will become a positive 1. Sorry, a positive 1. And 1 times I, then our answer is I. So as you can see, any power can be simplified. Doesn't matter how big or how small it is, I can simplify it. So this is something that you will have to be aware of. Okay. Now, if we move on, a complex number is any number that can be put in the form. Right? A complex number is any number that can be put in the form A plus BI. And we say that A and B, both A and B, okay, are real numbers. But I, okay, I is equal to the square root of negative 1. the form, okay, the form a plus bi is what we call standard form. Standard form of complex numbers or for complex numbers. And you will notice that sometimes or all numbers can be written this way, because if you don't see an I, it just means that B is 0. Okay? So A is generally what we call the real part. Okay? A is what we call the real part, and B is called the imaginary part. So A plus BI, okay? A plus BI, we say that this part here is the real part, and this part here is the imaginary part. So complex number has a real part and an imaginary part to it. Now you will hear that, and it's very often you may hear that every real number is a complex number. And that may sound weird to you. Every real number is a complex number. And the reason we say that, okay, the reason we say that is because if we have 5, okay, 5 is a real number. But that real number is also a complex number, because I can write this, can be written as 5, okay, plus 0i. Okay, 5 plus 0i. So here we have the real, and this part is my imaginary. But we don't write 0i, it has no meaning to or significance of writing it. But just to show you that a real number can be written as a complex number. Okay? And this happens for any real number. The same we can do the same for even pi. Pi. Yeah. Pi is an irrational number, but it's a real number, is real and irrational. And this can be written as pi plus 0i. Yeah. So it doesn't matter if it's real, it can be written as a complex. Real numbers can be written as complex. So we've kind of got the basics done, and now we can jump into some operations with complex numbers. So let's look at what is called equality for complex numbers. Yeah. And we'll start off this by saying two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. Okay. So let's think of things that we know. We start out 5 is equal to 5. Okay. 5 is definitely equal to 5. Okay. Likewise, we can say that A is equal to C if A, B, and C is some real numbers. Okay. If they represent some real numbers. Or we can say that A plus BI is equal to, okay, C plus DI, and this is true if and only if and only if A is equal to C and B is equal to D, right? So this is what's being drawn out here. These two things have to be alike because that's the real part, okay? And in addition, the imaginary part must be alike, okay? That's the only way this is equal. So how does this help us? Well, it does if I ask you to find x and y if 3x plus 4i is equal to 12 minus 8yi. So the first thing we want to do is, this is the real and this is the real. Anything that involves I is imaginary, okay? So if we break this up into the real and then we look at it into the imaginary, okay? So the real part, we have 3x is equal to 12. For the imaginary part, we have 4i is equal to minus 8yi. So here we can find x, and here we can find y. And to find x, we can divide both sides by 3. So 3 divided by 3 is 1, so x is equal to 4. Okay, and likewise here, the i's can cancel out, so we have 4i is equal to minus 8yi. This can cancel with that one. It's on both sides, or we can divide both sides by I. So we're left with 4 is equal to minus 8y. And to get y by itself, we can divide both sides by negative 8. And if we do this, the negatives will cancel, leaving you with 4 over 8. Negative 8 divided by negative 8 becomes positive 1. And we write the y. And this here can be simplified as 1/2. So we were able to solve for x and y, okay, based on the fact that the real part must be equal to the real part, okay? And the imaginary part must be equal to the imaginary part. So that's the idea we use when we do this. Let's look at one more example. Find x and y. So if we have 4x minus 3 plus 7i, that is equal to 5 plus 2y minus 1 times I. So if you look at the problem, you will observe that there's no I here, so that has to be the real part. And there's no I on this side, so that's my real part. So the real part here, the real, is 4x minus 3, and that is equal to 5. Okay. The imaginary part, is the part that has the i's. So here's the piece with I, and here's the piece here with I. So the imaginary part is 7i, and that is equal to 2y minus 1 in parentheses times I. And now we can solve for x and y. So we'll start out by adding 3 to both sides. And if we do this, we have 4x, the minus 3 and the plus 3 cancel out, and 5 plus 3 is 8. And then we'll divide both sides by 4. Okay. And we have 4 divided by 4 is 1, and 8 divided by 4 is 2. Okay. So x is equal to 2. Now, we're not finished. We also have to find whatever y is. Okay. To find y, we will start out by observing that the i's can be cancelled, right? So we end up with 7 is equal to 2y minus 1. If you want to put it in parentheses, that's fine. And if we do this, we can now solve for y. Because we don't need the parentheses, I can start off by adding 1 to both sides. And if I do that, I have 7 plus 1 is 8 is equal to 2y. The minus 1 and the plus 1 cancels out. And I can now divide both sides by 2. And that will give me 8 divided by 2 is 4. And the 2 divided by 2 becomes 1y. And I'm able to find y. So we're able to solve for x and y using this idea. Now, this would help us, or if we look at it further, we're able to add and subtract complex numbers. Complex numbers can be added and can be subtracted. Yeah. So to add and subtract complex numbers, yeah, we add the real parts or subtract the real parts, and add or subtract their imaginary parts. Okay. So we add or subtract with the real, and then we add and subtract the imaginary. So for example, if I have a plus bi plus c plus di. So here we have two complex numbers. So here is the real, and here is the real. So we can say that this is equal to a plus c, okay? And then we have the imaginary parts also, bi and di. And this is equal to, or we can say plus now, so this is the real, the imaginary is bi plus di. And sometimes we take it, we can simplify or write this a different way. We can say that this is b plus d parentheses I, where you clearly see that that's the imaginary part. Okay, clearly you see that that is the imaginary part. And the same goes for subtraction, right? So this is for addition. For subtraction, we do the same thing. If we have a plus bi minus c plus di. So in this case, the real part, okay, we say a minus c now plus, or the bi, okay, minus di. So keep in mind we get a minus here because if you distribute, that will be a minus. And we can say that this is a minus c plus b minus d, and I goes on the outside. So don't get frustrated with the notations. When you see the way it's work, it becomes just like adding and subtracting polynomials. Yeah. So let's look at an example. If I say add or subtract. So the first one we have is 3 plus 4i plus 7 minus 6i. So the real part is 3 plus 7 plus, okay, the imaginary part is 4i minus 6i. And I know 3 plus 7 is 10, okay? If we add the 3 plus 7, we get 10. Plus, if we take out the I, we have 4 minus 6, put the I on the outside. And 4 minus 6, we have 10 plus 2i. And here is the final result. So it's just a matter of combining like terms. Okay. If you look at another example, how about if I have 5 minus 2i minus 9 minus 4i. Okay. So as I said, think of this as polynomials, right? So if you want to get rid of the parentheses, right, this becomes 5 minus 2i minus 9 plus 4i, right, when you distribute. And then you combine like terms, okay? Combine like terms. So 5 minus 9, okay? And 5 minus 9, we know, is negative 4, okay? And then we have minus 2i plus 4i, and that becomes positive 2i. So it's really the same as adding or subtracting polynomials, right? And we could have done that over here too. Yeah, we could have done that, just get rid of the parentheses. So addition, subtraction, multiplication, and division is very similar to the way we work with polynomial. We just have to remember, okay, in multiplication and division, that I square represents something and I represents something, right? So there's not too much to really do with addition and subtraction. Okay? So let's move on and look at multiplication of complex numbers. So for multiplication, the idea is very similar, okay, to multiplying polynomials. So if I say multiply, and I give you 3 parentheses 5 minus 4i, well, you will distribute very similar to if you were distributing. So 3 times 5, that becomes 15, and 3 times minus 4i becomes minus 12i. And there's nothing to simplify here because it's the real minus the imaginary. On the other hand, if I give you 2 binomial, such as 3 minus 4i and 2 plus 5i. So you know if you have 2 binomial, we can FOIL this out. Okay. We multiply 3 times 2, which is the first term, so that becomes 6. Then we multiply 3 times positive 5i, and that becomes positive 15i. Then we multiply minus 4i times 2, and this becomes minus 8i. And then we have minus 4 times positive 5i. This becomes negative 20i squared. Okay. So I times I becomes I squared. Now simplifying this, we have 6. These are like terms. Okay. So 15i minus 8i becomes plus 7i minus 20. But remember, I square we established before, I square is minus 1. Okay? Whenever we see I square, we write minus 1. So now we have 6 plus 7i minus 20 times minus 1 becomes positive 20. And now we have like terms. These are considered like terms. So 20 plus 6 becomes 26 plus 7i. So the whole multiplication process, okay, is very similar to that as polynomials. Very similar. If we look at another example, yeah. But if we have an ask to expand 3 plus 5i quantity squared. Now remember that square means write the parentheses twice, right? Please do not distribute the power. So 3 plus 5i and 3 plus 5i. And here we apply the same as we did before. We FOIL it out. Yeah. So by distributing 3 times 3, which becomes 9, then we have 3 times 5i, positive 5i, and that becomes plus 15i. And then we move on and we set 5i times 3, and that becomes again plus 15i. And then finally 5i times 5i positive, that becomes positive. 5 times 5 is 25. I times I becomes I squared. Okay. We combine the like terms here. So this leaves us with 9 plus 30i plus 25. And don't forget, I squared is minus 1. So that leaves with 9, yeah, plus 30i. The plus and the minus becomes minus 25. And 9 minus 25, like terms, this becomes minus 16 plus 30i. Multiplication is very, very similar. Yeah, very similar. Now, the whole idea of division, the division process, is where we talk about sort of writing in standard form. Okay, so let's look at division now. So when we talk about division, we're really sort of asking you to write this in standard form. Okay. So if I ask you to divide 2 plus I divided by 3 minus 2i. So we want a complex number in standard form. And remember, standard form is really a plus bi, where we write the real and the imaginary. So we need to eliminate I from the denominator. Okay. So in this case, what we do, and you have seen this before, we multiply by the conjugate. So try to write 2 plus I over 3 minus 2i, right, in standard form, which is a plus bi, right? The real and the imaginary. Okay. So to do this, we will multiply by its conjugate. We will multiply this by the conjugate, which is 3 plus 2i. Because there is no way you can split that and write the I separate from the real part. Now notice, as we did, this is difference of squares. So when you multiply out the bottom, you will get 3 squared minus 2i quantity squared. Huh? And if you distribute the top using FOIL, you will get 6, okay, plus 4i plus 3i plus 2i squared. Okay. So we obtain that by multiplying these two. Okay, you know how to FOIL. Simplifying and combining like terms. So we have 6 in the numerator. Combine the like terms. 3i and 4i becomes plus 7i plus 2, and I squared is minus 1. In the denominator, 3 squared is 9, and then minus 4i squared, because scrap 2i quantity squared means 2i times 2i, which is 4i squared. So we have in the numerator 6 plus 7i minus 2, and in the denominator we have 9 minus 4 times negative 1. In the numerator, once again, we have like terms, so 6 minus 2 becomes 4 plus 7i. The denominator, we have 9 plus 4. So we have 4 plus 7i over 13. And now we can write, okay, write in standard form. In standard form, this becomes 4 over 13 plus 7 over 13i. So here we have the real and the imaginary part, okay? This part here is the real. This part here is the imaginary part. They're separated. Okay, the real and the imaginary part. And this is what we do when we have to write or divide. Now, not in all cases you will have to multiply by the conjugate, right? Not in all cases you're going to have to multiply by the conjugate. We had to because there was no way to separate these i's from this. Cannot be done. And every problem is different. Okay? If you look at this example, and I said to divide, okay, 7 minus 4i over I. Well, no matter what you do, okay, no matter what you do, you cannot separate the real from the imaginary, right? You will not be able to separate the real from the imaginary. So we have to multiply here by conjugate. Okay. So the conjugate, and this is important, right? The conjugate of I is minus I. So we have 7 minus 4i over I, multiply that by minus I, top and bottom. That's the conjugates. And if you multiply the denominator, okay, by multiplying the denominator, this times this becomes minus I squared, right? Minus I squared. And in the numerator, if we multiply 7 times minus I, becomes minus 7i. And then minus 4i times minus I becomes positive 4i squared. So if we simplify, we know that I squared is minus 1. So we have minus 7i plus 4 times minus 1. And in the denominator, we have a minus times a minus 1. Okay? Because I squared is minus 1. So we have minus 7i minus 4 over 1. Which is the same as minus 7i minus 4. But in standard form, the real part is written first. So this becomes minus 4 minus 7i. And here is our standard form. So this will take some practice, but it's based a lot on polynomials. addition and subtraction of polynomials based a lot on that. Okay. So as always, you need to practice more examples so you become better at this.